Okay, working on 13.5, which is curl and divergence. And on this problem, number 3, they give us a vector field. It's three-dimensional, and we're asked to find the curl and the divergence. So I'm going to start with the curl. The curl is defined to be the gradient or the del operator crossed with f, which means we're going to do a cross product. So I'm going to set up my cross product here. We're crossing del, which is the partial with respect to x, partial with respect to y, partial with respect to z, with f, but f is x, y, e to the z, 0, and then y, z, e to the x. And so we know that when we do a cross product, we get a vector. So I cover up the first column, and I do a little determinant right here. So I'm going to do this partial of this minus 0 times that. So we're going to have the partial, this will be a vector, so it'll be the partial with respect to y of y, z, e to the x minus 0, and then the partial, well, you could look at it this way. Here and here is really just the partial with respect to z of 0. And then we look at the middle one. So the middle one, we cover up this middle one, and we do the determinant again, but we subtract. So it'll be this, partial with respect to x of this, minus partial with respect to z of this, but then switch the signs. So I'm going to write that here. It's negative partial with respect to x of y, z, e to the x. And then it'll be minus, minus, so it'll be plus. And now I'm covering this up here and here, so partial with respect to z of x, y, e to the z. And then my last component, which I may not be able to get on here, I cover this up. I do here to here, which is 0, minus here to here. So I'm going to have negative partial with respect to y of x, y, e to the z. All right, so let's go ahead and figure out what this is. We have the partial with respect to y of this, so y is our variable. This is all a constant. Derivative of y with respect to y is 1. So I get z e to the x minus 0, so that's not there. And here, partial with respect to x of this. Cover up the yz, derivative of e to the x is itself. So I'm just going to have negative yz e to the x plus the partial with respect to z of this. Again, x and y are constants. Derivative of e to the z is itself. So I have plus xy e to the z. And then partial with respect to y of this. X and e to the z are constants. Derivative of y is 1. So we get negative x e to the z. So that is the curl of f. Just double checking. I had a long night last night. I'm tired. Okay, so that's our curl. Now we want to do the divergence, div f, which is almost the same formula except it's del dotted with f. So this time we're taking del, which is the differential operator, partial with respect to x, partial with respect to y, partial with respect to z, and we're dotting that with the field. Okay, e to the z, 0, y, z, e to the x. So we do this and this, which would be equal to, remember the div is going to be a scalar, it's not a vector, so we're going to get partial with respect to x of x, y, e to the z, plus partial with respect to y of this, which is 0, that's just going to be 0, plus partial with respect to z of y, z, e to the x, and this is just going to be y, e to the z. This is 0. This one is plus y e to the x. And there's actually 2 of those. I didn't notice that. Oh no, sorry, those are different. You could factor out a y. That's what the book has, but okay, pretty straightforward. This is just computational. Let me see if there's anything ugly, because I assigned 1 through 7 odds. Okay, I'm working number 5 now, and I kind of wrote a bunch of stuff down here already to save myself some time. Here's our field, and then we want to find the curl. So to find the curl, we set up this cross product computation. So I've got my del across the top and then my f here on the second row, and then I'm going to get my cross product. So I cover this up. I do the partial with respect to y of this, which is here, minus the partial with respect to z of this, which is here. It's the first component. Second component, I cover this up, and remember that it'll be negative of this determinant. So partial with respect to x of this, but negative, and then partial with respect to z of this, but positive. And then we have, cover up this, partial with respect to x of this, minus partial with respect to y of this. Now let me go ahead and do these. And to do these, I just want to show you something. With all of these, when I'm doing the partials, here it's with respect to y, I have a z on top, which is going to be treated like a constant. Partial with respect to z, I have a y on top, which is going to be treated like a constant. Partial with respect to x, and then a y on top, so y is going to be treated like a constant. Z and x, so x is a constant. X and y, so y is a constant. Y and x, so x is a constant. So I just want to look at, real quick, what would the partial derivative, let's say with respect to x be, of some constant over the square root of x squared plus y squared plus z squared. I'm doing this just to save myself time. Well, the constant doesn't matter, so I can pull that out times, if I rewrite x squared plus y squared plus z squared, the root on the bottom, I bring it up, this is negative 1/2. And now when I take the derivative of this, c doesn't matter, so I have c. The negative 1/2 pops out, negative 1/2 c. And then all of this, I'm going to subtract 1 from the power, so I get negative 3/2. And then times the derivative of what's inside with respect to x in this case, which would give me 2x. And then this 2 and the half cancel out, and so I'm left with negative constant times x, then all of this to the negative 3/2, which I'm going to write as over all of this to the positive 3/2. So what I'm trying to get you to notice is that if we don't care about the top, if it's going to be a constant, because this variable is going to be different, then at the end of the day, all you get is negative, and then whatever this constant was, and then whatever the variable was, right? Because if this was a y, when we took the derivative bottom, we would have got a 2y out here. So we're going to get whatever that variable is, okay, and then over that whole thing to the 3/2. That should be the pattern for all of these. So with that in mind, let me run through these derivatives, okay, one at a time. So this should be equal to the vector. All right, so I know I'm going to get a negative, the constant on top, which for us is z, the variable that I'm differentiating with respect to y, over all of that to the 3/2, which I'm going to call all that junk to the 3/2, minus, same thing here. Y is like a constant, so I get negative y, then the variable I'm differentiating with respect to z, over all that junk to the 3/2. Okay, over here, you've got to be a little careful here because I have a negative sign out here. I know that y is like the constant, so I'm going to get negative y, and then I'm differentiating with respect to x over all that junk to the 3/2, but I'm taking the negative, so this becomes positive, like that. And then I have plus, Again, x is like my constant, so negative x. Z is my variable, so z all over all that junk to the 3/2. Moving over here, y is like my constant, so negative y. X is my variable, all that junk to the 3/2. Minus, and I'm going to have, remember, x is like a constant, so negative x. Variable is y, and then all over that junk to the 3/2. So there it is. But notice that they all have the same denominator, so I can combine things together. So if I put these two together, notice that the numerator is going to become negative zy, and then negative negative plus yz, all over that junk to the 3/2. But this is 0 on top. They cancel out. So I get 0. So this is just the 0 vector. I mean, sorry, a 0 there. And then when I do the next one, which is this one, I get the same thing to happen. This and this cancel. So I get a 0 there. And then last one, this becomes a plus, and I get negative yx and plus xy. Those cancel again also. I get 0. So my answer is the 0 vector. So that's my curl. Now let's get my div. Div is always a nicer computation. Div f is del dot f. So I'm going to go through this one a little faster than I did the last one. It's the partial with respect to x of this, partial with respect to y of this, partial with respect to z of this. So I'll add it together. So let me look at that first one. What would the partial with respect to x of, I'm going to write x times x squared plus y squared plus z squared to the negative 1/2 be? Now I'm going to have the same pattern for all of these, all right? So let's see what I get here. I have a product rule. So this is going to be 1 times this. So x squared plus y squared plus z squared to the negative 1/2 plus, now derivative of this times this. So I'm going to have the x there. But then derivative of this, we already saw that a second ago, is negative 1/2. It was all of that stuff to the negative 3/2. And then times the derivative of what's inside of here with respect to x would be 2x. And I get sorry, didn't mean to cancel the x there. The 2.5. So I just get here, let me rewrite it, 1 over root x squared plus y squared plus z squared. And then this is going to be a minus. The x and the x together is x squared. And then I have all of this stuff to the 3/2. So that's what I would get if I did the derivative with respect to x. If I do it with respect to y, if I do this one with respect to y, then I'm just going to put y here. Everything comes out the same except that'll be y squared. If I do with respect to z on this one, it's all the same thing here, except I'll get a z squared here. So my div should be 1 over square root of x squared plus y squared plus z squared minus x squared over all this to the 3/2. That's the partial of this with respect to x, plus partial of this with respect to y should be, again, this thing, but with the y squared here. So 1 over square root x squared plus y squared plus z squared minus y squared over, I'm just going to say all that junk to the 3/2, okay? Plus the last one, 1 over the square root of all that junk minus z squared over all that junk to the 3/2. And you'll notice that the things that have the same denominators I can put together, so this, and this, I can put together. There's 3 of them, so when I add them up, I get 3 of these square roots of x squared plus y squared plus z squared. And then I have this, this, and this all have the same denominator, and they all have a negative, so I'm going to factor a negative out. And when I put them together, I'll get x squared plus y squared plus z squared over x squared plus y squared plus z squared to the 3 halves. And notice that this is the same as to the 1. And so if I do 1 minus 3 halves, I get negative 1/2, which is the same as all of that to the drop it down to the positive 1/2. So I get 3 over square root of x squared plus y squared plus z squared minus 1 over, again, I hope you see what I'm saying here. This turns out to be x squared plus y squared plus z squared. 1 minus 3 halves is negative 1/2, which means you drop it down. So this is going to be the square root of x squared plus y squared plus z squared. These are the same denominators. 3 minus 1 is 2. So we should get a final result of 2 over square root x squared plus y squared plus z squared. That's our div. All right. I think you can do the rest on that. You see 11. Through 15. Odd, so let me do 13. So 13 is we get a vector field 3x y squared z squared and then 2x squared yz cubed and then the last component is 3x squared y squared z squared. Now this question says determine whether or not the vector field is conservative. If it is conservative, find the function little f such that capital F, the vector field, is the gradient of little f. So let me see, 15. Yeah, okay, it's going to take a little bit. So what I need to do is check what's the curl of this first. So is this conservative? That's the same as saying is the curl of f equal to 0, right? That's what I want to know. So let me calculate the curl. To do this, partial with respect to x, partial with respect to y, partial with respect to z of the components 3x y squared z squared, 2x squared yz cubed, 3x squared y squared z squared, which is, I'm going to do my cross product here. So I'll cover those up and do this. So I'm going to actually do this one more mentally. Covering this up, what's the partial of y with respect to this? Well, x's and y's are constant, so derivative of, x's and z's are constant. Derivative of y squared is 2y. So I'll get a 6 x squared y z squared minus, now I do this and this, partial of this with respect to z, the 3 pops out, I get 6 x squared yz squared. 6 x squared yz squared. And you can notice already that is 0, so that's a good sign. And then, this is a curl of the 0 vector. I forgot to put that up there. I hope that's what I have in my notes. All right, so now the next part I cover up the middle one and I do the negative of this. So partial of this with respect to x would be 6x, but it's going to be negative, so negative 6x y squared z squared minus, right, but then subtract, I'm sorry, subtract negative, so it would be plus, and then I'm doing this and this, so the partial of this with respect to z is going to be 6xy squared z. Is that right? Hold on. Did I do this one? Cover up this. Partial. Forgot to bring the power on z down. Sorry. That was here to here. So now this one and this one, we get plus 6x y squared z. Oh, you know what? Hold on. This is right. Did I write that down right? Let's see. Make sure I wrote this down right. Which one was this? 13. 3xy squared z squared. 2x squared yz cubed. 3x squared y squared z squared. 3x y. Okay, so I got to run through this real quick. I know the first one worked. Cover up this. Cover up the middle one. Partial with respect to x of this. 2 comes 6 y z squared. That's right. And then partial with respect to z of this. 6x y squared z. I'm not getting my zero vector here. What's going on? Oh, okay. I apologize. I was looking at the wrong problem. Yeah, the curl's not going to be 0. Okay, so this was right. I was doubting myself there for a second, but I was looking at the next problem, in which the curl is 0, and I was like, what? This curl's supposed to be 0. So let me just double check that I have this. Okay, so, and then I can go on. Who cares what this is, right? This right here is not equal to 0, so there's no way this can be the 0 vector. So this is not a conservative vector field. Again, my apologies. Let me get you one that is. All right, let's do 15. I thought when I was looking at it, I thought I grabbed one where we did have a conservative vector field. So that's why I was kind of doubting myself there. 15. 15 is a conservative vector field, but we'll have to verify it. So for 15, I have our vector field is e to the yz, and then xz e to the yz, and then xy e to the yz. So is this conservative? So I want to know, is the curl 0? Is curl of f equal to the 0 vector? Well, setting everything up, partial with respect to x of e, let's see, e to the yz, partial with respect to y, partial with respect to z, okay, xz e to the yz, xy e to the yz, which is the vector. So covering up here, partial with respect to y of this, we have some product rule in there. So we have to do a product right there. So let me do that right below it. What is the partial? Well, I'll write it in here. What is the partial with respect to y of xy e to the yz minus, so I'm doing determinant here, did this part, and now I'm going to do minus that part. So partial with respect. I'm so sorry that I seem scattered today. I'm running on fumes right now. That's the first part, comma. Now, the next part, we cover up the middle and we do this determinant, but then we subtract it. So it'll become minus the partial with respect to x of x, y, e to the yz, and then it'll become plus this guy right here, partial with respect to z of e to the yz. Then I have another component, I'll put it down here, a little more room. It'll be partial with respect to x of x, y, e to the yz minus partial with respect to y of e to the yz. So I just did this minus this. Ah, shoot. I just noticed something. I put z right there. That should be z. Good thing I caught that now. Just double check everything else. And partial z. Okay. Let's see what happens. This equals the vector. Partial of this with respect to y. So this is where I was saying we have a product rule right here. So derivative of this with respect to y is x times e to the yz plus, now derivative of this with respect to y, which is going to be z e to the yz, but then finishing off product rule times xy. So we have x e to the yz plus xyz e to the yz, then minus, okay, this with respect to z, so another product rule there. The derivative of this with respect to z is x times e to the yz plus the derivative of this with respect to z, which is y e to the yz times the first part xy, or sorry, xz. And so you put those together, you get xyz, e to the yz, and then you have x e to the yz. So minus x e to the yz plus xyz e to the yz. And these are exactly the same, so those are going to cancel out. That's 0. That's good. Well, I just erased the last part I needed. Okay, partial with respect to x of this one. This one's easy, and it's negative. So negative y e to the yz plus the partial of this with respect to z. Yeah, okay, so I have this right here. Z's up here, derivative e to the yz, a y is going to pop out, and then we have e to the yz. These two are the same, and they're opposites and they cancel. And then the last one, which I just erased, I'll write it up here again. It was that last part, so I covered this up. So it was the partial with respect to x of x z e to the yz minus the partial with respect to y of e to the yz. So if I take the derivative of this with respect to x, since x is here, I don't have any product rule, it's just going to be z e to the yz. If I do derivative of this with respect to y, the z pops out and it's negative, so negative z e to the yz. Those are 0, so you get the 0 vector. So is it conservative? Yes. It is a conservative vector field. Now that we know it's conservative, they want us to find the little f such that the gradient of little f is equal to this capital F. So this is where I'm going to use partial integration. So here's what I know. Since this is the gradient, since this is conservative, I know that this part right here is the partial with respect to x of the scalar function f. This is the partial with respect to y of the scalar function f. And this is the partial with respect to z of the scalar function f. So beginning with this first piece of information, knowing that the partial with respect to x of the scalar function f is e to the yz, then if I integrate both sides, right, with respect to x, that'll give me f. So f will be equal to the integral of this, which is the integral of this with respect to x. And since x isn't in here, that's just a constant. So this is going to be x e to the yz. That's what f is, plus some constant of integration. But we talked about in class that this right here can actually have y's and z's in it. So I'm going to call this g of yz. It's some function of y and z, possibly, that I don't know. So that's what f is, little f, so far. Little f is x e to the yz plus some function of y and z. Now what I do is I say, all right, I know that when I take derivative of this with respect to y, I should get this. So what is the derivative of that with respect to y? Well, x is a constant. Up here we have to take derivative of e to the yz, which is going to give us x. Then the z is going to pop out, e to the yz. We know that plus the derivative of this with respect to y, which is that, must equal this, x z e to the yz. And notice these are the same. They cancel. And so partial of g with respect to y is 0. And if we integrate both sides with respect to y, I'll get g. So the antiderivative of 0 is going to be a constant, but g could have had z in it. So this means that g has to be some function of z only. So here's where I am. I actually know that f, little f, must be x e to the yz plus only some function of z. Now I use my last piece of information. I know if I take the partial of this with respect to z, I should get that. So the partial of this with respect to z, I'm just going to write it. Partial of that with respect to z is going to be, let's see, x, and then partial of this with respect to z, the y pops out, e to the yz, plus the derivative of this with respect to z, which is this. That must equal this piece, x, y, e to the yz. Again, these two cancel, and so you get partial of h with respect to z must be 0, and that means h must be a constant. And it can't have y in it because we said that h could only have z in it, so it's just a constant. So my final result is that the scalar function f, okay, the potential function, is this plus a constant. Whew, okay. That was a little bit involved. So I'll let you do the rest of those. Let me see, 21 and 23. 21 and 23, I'm not going to do. I'm going to let you do those on your own. All right, that's it for this section.